Welcome to the Deep Dive. Today we're tackling a huge topic, one that, well, underpins almost everything else we talk about in science and technology. Materials science.
It really does. It's kind of the science of stuff, isn't it? What things are made of, why they behave the way they do. We're talking solids, mostly, but sometimes liquids, even gases used for specific jobs.
Exactly. The science of what everything is made of. And our mission today, using the great sources you pulled together, is to give you a really solid, fast-paced overview. Core concepts, the history, where it's all heading.
Yeah, we want you to walk away understanding the language, how material scientists think about creating something new or improving something old. It's fundamental to, well, all engineering.
Okay, first things first. There's material science and materials engineering. They sound similar, but there's a key difference, right?
Absolutely. Think of material science as the deep dive, the research part.
Yeah.
Understanding why a material has certain properties, looking at its atoms, its structure, the fundamental knowledge.
In engineering.
That's the application side. Taking that science and figuring out, okay, how do we use this? How do we make it reliably, cheaply for a specific product or industry? They absolutely have to work hand in hand.
Got it. And there's a central concept, almost like a mantra for the field. We called it the materials paradigm.
Yes, the materials paradigm. It's crucial. It's this chain. Processing leads to structure, which determines the properties, which then dictates the final performance.
Processing, right arrow structure, right arrow properties, right arrow performance.
Okay. Change any step, and you change what comes after, especially that first step, processing. How you make it defines everything else. It's the lever you pull.
And this isn't just like a modern lab idea. This relationship, this paradigm, explains why history unfolded the way it did, doesn't it? You look at the Bronze Age, the Iron Age.
Precisely. Moving from one age to the next wasn't just finding a new rock. It was about mastering a new process that allowed control over the material structure, giving you better properties, maybe harder or stronger or easier to shape, which led to better performance in tools, weapons, everything. It's that constant cycle.
So let's dig into those roots. Where did this thinking actually start? It feels modern, but people have been working with materials forever. Pottery, metal.
Oh, forever. The practical knowledge is ancient, absolutely. Trial and error, observation, add this, heat it like that, you get bronze. But the intellectual framework, that really comes out of the Age of Enlightenment.
Right, applying systematic thought.
Exactly. People started using the tools of early chemistry, physics, mechanics to figure out the why behind those old observations in metallurgy and mineralogy. Not just that it worked, but how it worked at a deeper level.
And as you said, those breakthroughs define eras. Stone, bronze, iron, steel. Each leap forward was about better processing, wasn't it? Controlling heat, purity.
Completely. Getting copper and tin pure enough, learning the right ratio for bronze, then figuring out how to get iron hot enough to work it, and later, crucially, learning to control the carbon content to make steel. Each step was a processing triumph, leading to superior properties.
Was there a key theoretical moment that really kicked off the modern field?
I'd point to Josiah Willard Gibbs, the American scientist, late 19th century. His work on thermodynamics was just revolutionary for this.
Thermodynamics, like heat and energy, how does that connect?
Gibbs showed that thermodynamic properties, things related to energy and stability at the atomic level, are directly linked to the physical properties you observe, like strength or melting point. He provided the mathematical tools to predict which material structures or phases were stable under certain conditions. It connected the microscopic world to the macroscopic world.
Okay, so the theory was developing. But when did material science become its own field, separate from, say, metallurgy or chemistry?
That really happened after World War II, sort of in the 1940s and 50s. The field exploded beyond just metals and ceramics. Suddenly, you had intense research into polymers, semiconductors, biomaterials, a completely new classes of stuff.
What drove that expansion?
A big part of it, at least in the U.S., was government funding, specifically from ARPA, the Advanced Research Projects Agency, now DARPA. In the early 60s, ARPA funded these interdisciplinary materials research labs at universities.
And the goal wasn't just basic science.
No, the goal was explicitly to push the boundaries, to design new materials for specific needs, especially defense and aerospace. It forced chemists, physicists, engineers to work together. It really cemented MS as a forward-looking, design-oriented discipline.
So bringing it to today, where does this knowledge become critical? I mean, beyond designing new gadgets.
Well, a huge area is forensic engineering. Failure analysis.
When things go wrong.
Exactly. When a bridge fails, or a plane part breaks, or an engine component gives out, Material scientists are essential. They have to meticulously analyze the failed part.
How do they do that?
They look at the processing history, the operating conditions, and crucially, the microstructure of the material near the failure point. Was it a manufacturing defect? Was it fatigue from repeated stress? Was it corrosion? Understanding the material's structure and properties is key to finding the root cause, preventing it from happening again.
That makes sense. And it brings us right back to that paradigm. Processing right arrow structure, right arrow performance. You keep emphasizing structure.
Because structure is king. The whole field is about understanding the relationships that exist between the structures and properties of materials. And we look at structure on different size scales. It's not just one thing.
Okay, break that down. What's the smallest scale?
We start at the atomic structure. We're talking angstroms here, 10 to the minus 10 meters. This is where it all begins. How individual atoms bond together, ionic, covalent, metallic bonds, and how they arrange themselves in space, which is crystallography.
So the type of bond and the arrangement, that sets the basic rules.
Pretty much. Things like electrical conductivity, magnetism, basic chemical reactivity, a lot of that is determined right here by the atoms and their immediate neighbors.
And in crystallography, you mentioned the unit cell.
Right. If you imagine building a crystal like stacking identical Lego bricks, the unit cell is the smallest repeating brick. It contains the fundamental pattern. Describe the unit cell, its size, shape, which atoms are where, and you've basically described the entire perfect crystal.
A perfect crystal, like you said earlier.
Exactly. Perfect crystals don't really exist outside of maybe a computer simulation. Real materials always have defects. Missing atoms, called vacancies, extra atoms squeezed in where they don't belong, called interstitials, misaligned planes of atoms, called dislocations.
And these aren't just annoying flaws.
Far from it. Often these defects control the most important properties. They're not bugs, they're features, you could say.
How so? Give me an example.
Okay, take metals. Why are they ductile? Why can you bend a paperclip instead of it just snapping?
Because it's metal.
Yes, but why? It's because of dislocations. Those line defects, those extra half planes of atoms. When you apply stress, these dislocations can move like a ripple through the crystal. That movement allows the planes of atoms to slide past each other without breaking the bonds completely. That's plastic deformation.
So the ability of metal to bend relies on these imperfections moving.
Precisely. If you had a theoretically perfect metal crystal with no dislocations, it would be incredibly strong, yes, but also incredibly brittle. It would shatter like glass. So material scientists spend a huge amount of time figuring out how to control the number and movement of dislocations to get the right balance of strength and ductility.
That's fascinating. The flaws are the key. And of course, not everything is crystalline, right? What about glass?
Good point. Some very important materials are amorphous. Glass is the classic example, many polymers too. They lack that long-range repeating order of a crystal. The atoms are sort of jumbled together, more like a frozen liquid. That gives them very different properties.
Okay, so that's the atomic scale. What's the next level up?
We move up to the nanostructure. This is the scale from about 1 nanometer up to maybe 100 nanometers. This area has just exploded in the last couple of decades.
Why? What's special about that size range?
Because when you make structures this small, the physics starts to change. A huge fraction of the atoms are now on the surface or very close to it.
The surface area to volume ratio goes way up.
Exactly. And that means surface effects, quantum effects sometimes, start to dominate behavior. Materials at the nanoscale can have totally different electrical, optical, magnetic, even mechanical properties compared to the same material in bulk form.
So how do you categorize these nanostructures?
We often talk about their dimensionality. If only one dimension is at the nanoscale, like the thickness of a coating, you get things like nanotextured surfaces or thin films. If 2 dimensions are nanoscale, like the diameter of a wire or tube, you get nanowires or nanotubes, like the famous carbon nanotubes.
And 3 dimensions.
Then all 3 dimensions are confined to the nanoscale. That gives you nanoparticles, which can be roughly spherical, or quantum dots, tiny little chunks of material.
Okay, atomic, nano, what's next?
Next up is the microstructure. Now we're talking from roughly 100 nanometers up to maybe millimeters, but usually viewed under a microscope, say, above 25 times magnification. This is the traditional realm of metallurgy and ceramics engineering.
And what defines the microstructure?
This is where we see things like grains. Most metals and ceramics aren't single perfect crystals, they're polycrystalline. They're made up of many tiny individual crystals, called grains, all packed together.
Like a mosaic of tiny crystals.
Exactly. And each grain might have a slightly different orientation of its crystal lattice compared to its neighbors. The boundaries between these grains, the grain boundaries, are really important.
Why? What do the grains and boundaries affect?
Oh, tons of stuff. Strength, how easily a crack can travel through the material, toughness, ductility, even corrosion resistance. It's a huge factor.
Is there a simple rule like smaller grains are better?
Often, yeah. Smaller grains mean more grain boundaries. And grain boundaries act as obstacles to dislocation movement, those defects we talked about. So generally, a material with a finer grain structure is harder and stronger. There's actually an equation for it, the Hall-Petch relationship.
So engineers carefully control grain size during processing.
Absolutely. Using techniques like heat treatment or specific alloying additions. And they use tools like microscopy and powder diffraction to check that they got the microstructure they wanted.
Okay, that covers the micro level. Is there one more scale?
Yep. The last one is the macrostructure. This is what you can see with the naked eye. Millimeters, centimeters, meters. The overall shape of the part, any visible cracks, porosity from casting, stuff like that.
So less about fundamental properties, more about the finished object.
Generally, yes. While large flaws are obviously bad, the real control over the material's intrinsic properties happens down at the atomic, nano, and especially the microscales.
Okay, we've got structure covered across all scales. Now let's link it back to the other parts of the paradigm. How do we actually control that structure? That brings us to processing, thermodynamics, and kinetics.
Right. Processing is the how you make it part. It's absolutely critical. You can design the most amazing material on paper, but if you can't make it reliably and affordably, it's useless industrially.
So this includes things like casting metal, rolling steel, welding.
Yeah, all the manufacturing techniques. Sintering powders together to make ceramics, growing single crystals for semiconductors, laying down thin films for electronics. It's incredibly diverse.
And you mentioned control is key. How precise does it need to be? Like, does a tiny bit of something else really matter?
Oh, absolutely. Steel is the perfect example. Steel is basically iron plus carbon, but whether it's steel depends on the carbon being between about 0.01% and 2.00% by weight. That's a tiny range.
Within that range.
Tiny shifts make huge differences. Low carbon steel, maybe 0.1%, is soft and ductile, easy to shape. High carbon steel, maybe 1%, can be made incredibly hard. Good for tools, but it's more brittle. Controlling that carbon content and other trace elements down to fractions of a percent is everything in steelmaking.
Wow. Okay, so processing sets the structure.
Yeah.
But how do we know what structures are even possible or how they'll change? That's where the other two come in.
Exactly. We need the laws of thermodynamics and the rates of kinetics.
Thermodynamics first. That's about energy and stability.
Right. Thermodynamics tells you what's possible from an energy perspective. Will this reaction happen? Will this phase transform into that phase at this temperature? It defines the stable states using concepts like energy and entropy. If a change requires too much energy input or leads to a much less stable state, thermodynamics says, nope, not going to happen spontaneously.
So it sets the boundaries, the rules of the game.
You got it. And the most practical tool that comes directly out of thermodynamics for materials scientists is the phase diagram.
I've seen those. They look like complex maps.
They are, but they map out which phases, solid, liquid, different crystal structures, are stable at different temperatures and compositions for a given material system, like iron and carbon for steel. They are indispensable for designing heat treatments and understanding alloys.
Okay, so thermo says if a change can happen, but not how fast.
Exactly. That's the job of kinetics. Kinetics is all about the rate of change. How quickly does that transformation actually occur? How fast do atoms move around?
Like your mountain climber analogy, thermo says you can reach the summit. Kinetics tells you if you'll get there before dark.
Perfect analogy. In materials, the most important kinetic process is usually diffusion, the movement of atoms within the material.
How does that work in a solid? Atoms are locked in place, aren't they?
Mostly, but remember those vacancies, those empty spots. An atom can jump into an adjacent vacancy, leaving its old spot empty. It's like a slow-motion atomic square dance.
Vacancy diffusion.
That's the main way atoms move around in solids. And it takes time, and it's highly dependent on temperature. Heat things up, atoms vibrate more. Diffusion happens much faster.
And this is crucial for processing.
Absolutely critical. When you heat treat steel, for example, you're relying on kinetics. You hold it at a certain temperature for a specific time to allow carbon atoms to diffuse where you want them, to allow the microstructure to rearrange into the desired state. Too short or too cold, and the change doesn't happen properly. Kinetics dictates the time element of processing.
Processing, guided by thermo and kinetics, creates the structure, which gives the properties and performance. It all fits. Okay, let's talk about the actual materials we use. What are the major categories?
Visually, we group them into three main families: ceramics and glasses, metals and alloys, and polymers. And then there's a fourth important category that overlaps: composites.
Can we make this relatable? You used a great analogy before the beverage container.
Right. It shows the trade-offs perfectly. Think about a glass bottle. Glass is a ceramic. Pros: it's transparent, cheap raw materials, keeps the fizz in, good gas barrier, recyclable. Cons: heavy, and it shatters easily. It's brittle.
Okay, then an aluminum can, metal alloy.
Pros: pretty strong for its weight, excellent barrier, recyclable. Cons: opaque, making it uses a lot of energy, it dents easily.
And finally, a plastic bottle.
Polymer. Pros: super lightweight, cheap to mass produce, doesn't shatter like glass. Cons: not as good a gas barrier. Your soda goes flat faster. So you see, no single material is perfect for everything. It's always about choosing the best set of properties for the job.
Makes sense. Let's dive into ceramics and glasses then. What defines them?
These are typically inorganic, non-metallic compounds, often oxides, nitrides, carbides. Think pottery, cement, glass, bricks. Their calling cards are usually hardness, stiffness, high temperature stability, good insulation, electrical and thermal, and often good wear resistance.
But the big drawback is brittleness, right? They tend to fracture.
That's historically been the main limitation, yes. They don't have those easily moving dislocations like metal, so when a crack starts, it tends to just zip right through.
But scientists have found ways around that. You mentioned crack deflection.
Yeah, this is a clever microstructural engineering trick. You embed strong secondary particles or fibers within the ceramic matrix. When a crack tries to run, it hits these obstacles and has to go around them.
Changing direction takes energy.
Exactly. It forces the crack down a longer, more difficult path, which absorbs energy and makes the whole material much tougher, less prone to sudden failure. It's a key principle in advanced ceramics, even in things like tough smartphone screens.
Like Corning's Gorilla Glass.
That's a great example of engineering the structure and composition to dramatically improve fracture resistance in a traditionally brittle material.
Okay, moving on to metal alloys.
Yeah.
You said iron alloys dominate.
By sheer tonnage, absolutely. Steel, stainless steel, cast iron, they're the workhorses of construction, automotive infrastructure.
And we already touched on steel iron plus carbon, controlled by heat treatment. Can you elaborate on that heat treatment process? Quenching and tempering?
Sure. So you heat the steel up high enough to dissolve the carbon within the iron's crystal structure. Then you quench it, cool it down really fast, usually in water or oil.
What does the rapid cooling do?
It traps the carbon atoms where they are, preventing them from diffusing out and forming softer phases. Instead, it forces the iron lattice to distort into a very strained, hard structure called martensite. It's extremely hard, but also very brittle.
Too brittle to be useful, usually.
Often, yes. So that's where tempering comes in. You gently reheat the quenched steel to a lower temperature, maybe a few hundred degrees C. You hold it there for a while.
Letting the atoms move a bit. Kinetics again?
Precisely. It allows just enough diffusion for some of the carbon to precipitate out as tiny carbide particles, and it relieves some of the internal stress in the martensite. The result is a material that's still very strong, but significantly tougher and more ductile. You trade a little hardness for a lot more toughness. It's a classic materials engineering balancing act.
Beyond steel, what other metals are important?
Well, for high-performance applications, especially where weight is critical, we look at alloys of aluminum, titanium, and magnesium. Think aerospace, high-end cars, performance bicycles.
Why those?
They offer fantastic strength-to-weight ratios. Titanium, for instance, can be as strong as steel, but is about 40% lighter. It's also incredibly corrosion-resistant, which is why it's used in jet engines and medical implants.
But they're more expensive.
Generally, yes. Extracting and processing them is more complex and energy-intensive than steel. Aluminum needs electrolysis. Titanium is tricky because it reacts easily. So you use them where the performance benefits justify the cost.
Okay, third family, polymers, plastics and rubbers. What's their deal?
Polymers are all about long chains. They're made of repeating molecular units called monomers, linked together into massive molecules, sometimes millions of atoms long.
And that chain structure gives them unique properties.
Definitely. The things like flexibility, low density, ease of molding into complex shapes. Their properties depend hugely on the type of monomer, how long the chains are, and how the chains interact with each other. Are they tangled like spaghetti, or can they line up more neatly?
You also mentioned versatility comes from additives.
Oh yeah, hugely. Take PVC, polyvinyl chloride. Pure PVC is rigid, used for pipes, but add plasticizers, small molecules that wedge between the polymer chains and let them slide past each other more easily, and it becomes flexible, suitable for things like vinyl flooring, wire insulation, or even shower curtains. Additives can change color, UV resistance, flame retardancy. It's like a molecular toolkit.
How are polymers classified?
Often by their application and performance. You have commodity plastics like polyethylene, PE, for plastic bags, polypropylene, PP, for containers, cheap, high-volume, disposable stuff.
Yeah.
Specialty plastics designed for specific unique properties, maybe high temperature resistance or unusual optical behavior, and then engineering plastics.
These are the high-performance ones.
Right. They offer superior mechanical properties, strength, stiffness, wear resistance, stability at higher temperatures. Things like polycarbonate, nylon, and a really interesting one, ultra-high molecular weight polyethylene, UHMWPE.
What's special about that one?
The polyethylene chains are just incredibly long, millions of repeating units. This creates a material that is remarkably tough, abrasion-resistant, and has an extremely low coefficient of friction.
So useful for things that need to slide or resist wear.
Exactly. It's used in industrial wear strips, conveyor belt parts, and famously as the socket liner in artificial hip and knee joints because it slides so well against the metal or ceramic ball.
Amazing. Okay, the final category, composites. What makes them different?
Composites are mixtures, but on a macroscopic scale. You take two or more distinct materials, often a reinforcing material, like fibers, embedded in a matrix material, like a polymer resin, and combine them to get properties better than either component alone.
So not like an alloy where elements are mixed at the atomic level.
No, you can typically see the different phases in a composite, at least under a microscope.
Yeah.
Think of glass fibers in a polymer matrix, or carbon fiber reinforced plastics used in aircraft and sports equipment.
You had a really dramatic example, the space shuttle material.
Ah, yes. Reinforced carbon-carbon, RCC. That stuff is incredible. It was used on the wing leading edges and nose cap, the parts that got hottest during re-entry.
How hot are we talking?
Upwards of 1,500 degrees Celsius. Just white hot. RCC could handle it.
How is it made? What's its structure?
It's a multi-step process, really clever engineering. You start with layers of graphite cloth made from rayon fibers. You impregnate this with a phenolic resin, cure it, then bake it at high temperature in an inert atmosphere. This pyrolyzes the resin, turning it into pure carbon, binding the cloth layers together.
So now it's basically carbon fibers held together by a carbon matrix, carbon-carbon.
Exactly. But pure carbon, while strong at high temps, burns easily in oxygen. So the final, crucial step was applying a coating of silicon carbide.
Why silicon carbide?
It forms a protective layer that resists oxidation at those extreme temperatures. So the silicon carbide protected the structural carbon for strength, the silicon carbide for protection to achieve performance neither could manage alone. A true composite solution.
That's incredible engineering. Okay, let's shift gears now to the cutting edge. Where is material science research focused today and tomorrow?
Well, we have to start with semiconductors. They're not new exactly, but the advances are constant, and they are the absolute bedrock of modern electronics. The whole digital world runs on them.
It's a massive industry.
Huge. Over $500 billion globally. And it all relies on materials whose electrical conductivity is somewhere between a conductor like copper and an insulator like glass.
And the key is controlling that conductivity.
Precisely. Using a process called doping. You start with an ultra-pure semiconductor crystal, usually silicon, and intentionally introduce tiny, tiny amounts of impurity atoms.
Impurities.
Yeah.
Like flaws again.
Sort of, but these are deliberately added. If you add an element with one more valence electron than silicon, like phosphorus, you get extra electrons that can carry current. That's N-type silicon. If you add an element with one fewer valence electron, like boron, you create holes where electrons are missing. And these holes can act like positive charge carriers. That's P-type silicon.
And putting N-type and P-type together
Yeah.
lets you build devices.
Exactly. The junction between N and P-type regions is the heart of diodes and transistors, the fundamental building blocks of integrated circuits. The ability to precisely control doping is everything.
Silicon is the king, you said.
By far. It's abundant, cheap, and its natural oxide, silicon dioxide, is an excellent insulator, which is incredibly convenient for making transistors, but it's not the fastest.
What's faster?
For really high-speed applications, like in your mobile phone's signal processing or in radar systems, gallium arsenide, GAs, is often preferred. Electrons simply move through GAs much faster than silicon.
Higher electron mobility.
Right. The downside is that GAs is more expensive and harder to process than silicon. So again, it's a trade-off cost versus performance.
Okay. Beyond semiconductors, what's hot? We talked about the nanostructure scale earlier.
Yes, and nanomaterials research as a dedicated field is booming, really focusing on exploiting those unique properties that emerge between 1 and 100 nanometers.
Like carbon nanotubes.
Carbon nanotubes are a prime example, along with graphene, which we'll get to, fullerenes, buckyballs, and various nanoparticles. Their potential is enormous: stronger composites, better catalysts, new types of sensors, more efficient energy storage. The list goes on.
Another really important frontier seems to be where materials meet biology.
Absolutely. Biomaterials science. This is all about designing materials that can interact safely and effectively with biological systems with the human body, usually.
So things like implants?
Implants are a huge part of it. Artificial joints, heart valves, dental implants, stents, but also materials for drug delivery systems, where a material might slowly release medication inside the body, or materials for tissue engineering scaffolds designed to help the body regenerate damaged tissues.
Does the body react to these materials?
That's the key challenge. You need biocompatibility. The material shouldn't cause harmful inflammation or rejection. Sometimes you want the material to be inert, just tolerated by the body. Other times you want it to be bioactive.
Bioactive, meaning it interacts chemically.
Yes. For example, coating a titanium hip implant with hydroxylapatite, a calcium phosphate ceramic similar to bone mineral. This encourages the patient's own bone cells to grow onto and bond directly with the implant surface, creating a much stronger, more stable integration. It's really sophisticated stuff.
And driving a lot of this progress is computing power, right?
Definitely. Computational materials science is transforming the field. We can now simulate how atoms and molecules interact, predict crystal structures, model defect behavior, calculate properties.
Yeah.
All before we even make the material in the lab.
Using techniques like molecular dynamics.
Molecular dynamics, density functional theory, powerful simulation tools. The big dream here is something called integrated computational materials engineering, or ICME.
What's the goal of ICME?
To link simulations across all the scales from atoms up to the final component with real-world experiments. The idea is to dramatically speed up the design process. Instead of years of trial and error lab work to develop a new alloy, maybe you can do most of the optimization on a computer in weeks.
Digital prototyping for materials.
That's a good way to put it. It promises to make the discovery and deployment of new materials much, much faster.
Okay, so with all this research power, what are some of the really exciting emerging technologies we should watch out for? Where does it get really interesting?
Well, the sources point to a few game changers. First, graphene. We mentioned it briefly. A single layer of carbon atoms arranged in a honeycomb lattice.
The thinnest material possible.
Pretty much. And it's incredibly strong, way stronger than steel, very light, and an amazing conductor of electricity and heat. The potential applications are just staggering.
Like what?
Faster transistors, maybe replacing silicon in some areas, flexible, transparent conductive films for touchscreens or solar cells, membranes for water filtration, high-capacity energy storage, efficient hydrogen storage for fuel cells. It's still early days for large-scale production, but the promise is immense.
Okay, what else?
Metamaterials. This is mind-bending stuff. These aren't materials defined by their chemistry, but by their engineered structure, usually on the micro or nanoscale. They're designed to interact with light or other electromagnetic waves in ways no natural material can.
Like the invisibility cloak idea.
That's the most famous potential application. Yes, materials that could bend light around an object, but also potentially revolutionary lenses, antennas, or materials that absorb sound or vibrations in unique ways. It's really about controlling wave propagation through structure.
Very futuristic. Anything else?
Quantum dots. These are those tiny semiconductor nanocrystals we mentioned earlier, just a few nanometers across.
And their properties depend on their exact size.
Exactly. Because they're so small, quantum mechanics dictates their behavior. Specifically, the color of light they emit when excited depends directly on their diameter. Smaller dots emit bluer light, larger dots emit redder light.
Where could that be used?
The most immediate application is in displays. Quantum dot TVs are already on the market, offering brighter colors and better energy efficiency than traditional LCDs. They're also being explored for high-speed optical communications, biological imaging, even quantum computing.
It sounds like the control over structure is reaching an incredible level of finesse.
It really is. And that brings us back full circle. The power of material science lies in that unified approach. Understanding structure across all those scales, atomic, nano, micro, and learning how to control it through processing, using the rules of thermodynamics and the timing of kinetics, all to achieve the specific properties needed for the desired performance.
So for you listening, the big takeaway here is just how fundamental this field is. If you're interested in any kind of engineering or technology, understanding materials is just essential. It connects physics, chemistry, mechanical engineering, electrical engineering. So it's a common language.
Every new material opens up entirely new possibilities. Think about how silicon changed the world, or how plastics revolutionized manufacturing. The materials we discover and engineer define what's possible technologically.
We've covered a lot: steel, silicon, polymers, composites, these amazing new frontiers. But let me leave you with a final thought, something to chew on. The sources make it clear this field is constantly evolving, driven by computation, by biology, by new physics.
There's always something new around the corner.
So think about the material we didn't name today. The one that's maybe just an idea in a simulation right now, or a curiosity in a biomaterials lab. What material, perhaps emerging from quantum science or AI-driven design, will be the next silicon? The one that defines the next great technological leap for humanity? That's the question material science is working on right now.
A fascinating question indeed. Thanks for joining us for this deep dive.
We'll see you next time on The Deep Dive.